Okay. How are better energy systems for making ATP? So first of all, our three macronutrients: proteins, carbs, and fats. Okay? Of these three, the only two that we're really going to be using for the purposes of making our energy are going to be carbs and fats. Okay, when we talk about our energy that we use in our system, it's always ATP. Anything that we take in and consume, we're going to convert into ATP. And we're going to do this by a number of different energy pathways. And there are 4 different energy pathways that we're going to use. And we'll talk about all 4 of them today in some capacity. Now, the difference between carbohydrates and fats in terms of why we would use one versus the other is the speed of combustion. Carbohydrates burn much faster than do fats. So let's put that in your notes first. Carbs burn faster than fats. That's just one of those mantras that you just need to know and say over and over and over again. Carbs burn faster than fats. Okay, so then the question must be asked, why would we even bother burning fats if they burn slower than carbs? The reason is because they contain more energy than do carbs. Okay, so fats are more energy dense than are carbs. Okay? And then there's a second reason why we would choose fats. And that's because we have so much more of them. Even the skinniest of skinny people has days worth of fat stored. Whereas the most that we can store in terms of carbohydrates is around 4 hours, and that's going to be a very well-trained individual who's very well fed as well. Okay, now the process by which we extract this energy out of our foods, okay, is by robbing electrons effectively. We're going to be taking these electrons out of these substances, and we're going to be using the energy in those electrons to be making our ATP. So, a few things that we want to point out here. For our 4 energy pathways, 2 of them are going to be what's called anaerobic, which means that they don't require oxygen. And then the other 2 are going to be aerobic, which means that they do require oxygen. And we'll get to which one is which in just a minute. Now, proteins we can use for the purposes of making ATP, but conditions have to be very severe. We have to be completely empty of carbohydrates, and almost all of our fats got to be gone. So under what circumstances would those be? Starvation. That's pretty much it. There are some times during very high intensity exercise where we start to metabolize a little bit of muscle tissue, but that's mostly because we're breaking down that muscle from eccentric contractions, and since it's floating around in the blood, we'll metabolize it. But we're talking a small fraction. Okay, we typically will not burn up fat unless we've completely run out of these 2, or at least run extremely low. All right, so let's move on to starting off with our carbohydrates. It says here it's our preferred fuel source for high intensity exercise, and we store this in the form of glycogen in 2 places, skeletal muscle and liver. Okay, so what we're looking at here is a micrograph of a biopsy from a calf muscle before somebody ran a marathon and then after they got done running that marathon. And what you can see here is that this is glycogen stored inside this muscle. It's right here. And then after the marathon is done, no glycogen left. Burn through all of it. Okay, so first of all, what fiber types of the 3 fiber types, what fiber types are going to store the most glycogen? Type 1s are going to use fats, so they're not going to be that one. The other end of the spectrum, the 2 X's. Those are going to be the ones that burn most of our carbs. Marathon runners probably have a lot of 2A, not so much 2X, but they'll still store quite a bit of carbohydrate. All right, it says we have 2 to 4 hours worth. This is going to be dependent upon feeding status. When was the last time you had anything to eat? And then also training status. So if you do a lot of aerobic training, you can increase the amount of glycogen that you can store in the body by quite a bit, but 2-fold. Now, look here, this is the actual structure of glucose. Now, glucose is the form of carbohydrate that we're going to use to make ATP. We store it as glycogen, which is this gigantic polymer of thousands of glucose molecules stuck together. But the base currency that we need in terms of carbohydrates is glucose. Any of the other sugars that we take in have to get converted to glucose first before we can actually metabolize them. So, if we look at this, we can see that this has 6 carbons. Everywhere we have 4 lines come together, that's where we have a carbon. So this is a carbon, 2, 3, 4, 5, and 6 carbons up here. So write this down. Glucose has 6 carbons. And the chemical formula for glucose, as well as the other monosaccharides, is C6H12O6. The most important part for you to remember is that it has 6 carbons. All right. Now, the glycogen that we store in the muscle is going to be used in this muscle itself. It's not going to leak out into the blood and be used by any other tissues. The first sign of when you reach fatigue is when you run out of muscle glycogen. At that point, you're going to be having to shift down in terms of your intensity, because the only fuel that you have left to you at that point that you can burn rapidly is going to be the fats that you have stored. And you have some that are intramuscular as well. If you run out of liver glycogen, which will happen later, then at that point you're just completely destroyed, because then you run out of fuel for your brain too. The brain really only runs off of glucose. It can't run off of fats because they're too big to go across the blood-brain barrier. The only other fuel that the brain can use are what are called keto acids, which will generate if you're on what's called a keto diet. All right, so here we have this number of 2 to 4 hours worth that we have stored up. This is an important number because once we run out of glycogen, obviously we hit that fatigue state. So when you see people who are very well trained, and this person is finishing a marathon at the end of an Ironman, okay, that's an enormous distance, but this marathon is at 2:20, that's a pretty damn fast marathon. Okay, that's well within that 4-hour range in terms of how much glycogen they have stored. So this person was able to run at their nice race pace the whole time and feel pretty comfortable. But if you've ever seen the finish line of a marathon when you get to like 4, 5, and 6 hours, you know, those folks don't look nearly as happy because they're much less trained, they had much less glycogen to begin with, and they ran out a long time ago. Okay, so they kind of look like this when they finish. Right? They've completely bonked, and all they have left at this point is fat. So that's the difference between those two conditions. So let's move on to fat. When we talk about fat, really what we're speaking about are called triglycerides, with its prefix tri meaning 3. Okay, so we have a fat molecule that's made up of glycerol here, and then 3 long chain fatty acids. We have glycerol and 3 long chain fatty acids. This is the preferred fuel source during rest and low intensity exercise. Okay, and again, the reason why we prefer to use this at rest instead of using carbohydrate is because it's got so much more energy in it. And since we don't need ATP as rapidly, we can burn this slower burning fuel when we're at rest and also low intensity exercise. All right, so we have our structure. 3 long chain fatty acids and a glycerol backbone. Now the glycerol we really don't use to do much with. Okay, it is the 3 long chain fatty acids that we're actually going to be metabolizing to make ATP. You have to metabolize these fatty acids in the presence of oxygen. Can't do this anaerobically. So this is going to be an oxidative process, which means oxygen has to be present. Okay, so of the 3 fiber types, which ones are going to be burning most of the fat? The ones that are oxidative. Which fiber types are oxidative? Ones. We have abundant stores of fat in a couple different places. We have subcutaneous fat, which is the fat that's just underneath your skin. We have intramuscular fat, which is just like it sounds. It's actually in the muscles. We can use that in those muscles. But the most abundant source of fat that we have is called visceral fat. And this is going to be inside our abdominal wall, and it lines all of our abdominal organs. Okay, so this is the most metabolically active fat. If you're trying to lose weight, it's the visceral fat that you're really trying to get rid of. Okay, unfortunately, it's the last to go, but it's the one that we want to get rid of the most. Now, each one of these is an adipocyte, a fat cell. What you can see is that there's not much in there except for this gigantic vacuole of fat. All of the rest of the cellular organelles are stuffed into just this one little corner here. So you'd have your nucleus, you'd have your endoplasmic reticulum, soft and smooth, you'd have your Golgi apparatus. Everything else would be smashed in that little spot. Now here's the pernicious thing about fat cells. Once they get filled up to a certain size, they can't get any bigger, so they mitotically divide and split. And then each one of those daughter cells can fill up again and get to its max size. And then they split. And it just keeps happening over and over again. Now, when you start to drain fat out of them, you can make each one of these smaller, but you can't make them go away forever. Okay, so you'll have that many fat cells if you're really, really big and lose weight that you can then refill later if you're not careful with your diet. And when this really happens, this rapid mitotic division of these fat cells is during puberty. So if you're kind of chunky during puberty, it's going to stay that way the rest of your life. You're going to be dealing with it forever. If you get to puberty relatively lean, you're in good shape pretty much thereafter. Okay, so that's the danger zone for development of obesity later in life. So why do we burn carbs and fats? We burn them to make ATP. So what is ATP? This is adenosine triphosphate. Okay, so adenine and ribose together is adenosine. So this nucleotide with this pentose sugar together is adenosine. And then we have 1, 2, 3 phosphate groups. Okay, so adenine and ribose is adenosine. And then we have our 3 phosphate groups. The energy contained in the bond between those phosphate groups is very high. And it is the breaking of that last bond that's going to then release energy. Okay, the purposes of these 4 pathways that we're going to then use to put this back together again is to get this inorganic phosphate to link back up with our adenosine diphosphate. Okay, so when we metabolize our foods, the whole reason we do that is to take ADP and turn it back into ATP. We want to recharge that battery. So when we break this last bond, that's how we release energy. We'll use that energy for muscle contractions. We'll use that energy to keep our bodies at a normal temperature the entire time. We'll use that energy to grow. So we need to have ATP at all times. So once that bond is broken, we have to reestablish it so that we can break it again. It's the burning of our carbs and fats that allows us to reestablish that bond so that we can break it again. So it's like we have to have a constant supply of food being metabolized to recycle our ADP back to ATP. Questions? Okay, so here are our 4 energy pathways. So let's split these in 2, right here. We have our phosphagen pathway, and we have our glycolysis pathway. These 2, I want you to write down 2 things about them. 1, they're anaerobic.
Which ones did you say? Sorry.
Top 2.
Okay.
Phosphagen and glycolysis are anaerobic, and they take place in the cytoplasm. Okay, so you're going to have a table that's going to be anaerobic versus aerobic, and then location. So the top 2 are anaerobic, and they take place in the cytoplasm. Here, I kind of combine these 2 together. They're actually separate pathways, but they're linked together. So Krebs and ETC, which we'll see later, this is aerobic. and beta oxidation is also aerobic. And both of these take place in the mitochondria.
What was the second part about oxygen, that they're anaerobic and what?
They're located in the cytoplasm.
And you said the last two are what?
They're aerobic,
Mm-hmm.
and they're located in mitochondria. All right, so what we're looking at here is a series of different athletic events that take a different duration of time to complete. Okay, and then we're looking at each one of the energy pathways in terms of their percent contribution, depending on how long the event is. If something is really, really short, okay, 0 to 10 seconds in that range, the majority of the ATP that we're going to produce is going to be coming from the phosphagen system. Once we get past 10 seconds and we're going on to about a minute, minute and a half, then the majority of the ATP we produce during an event like that is coming from glycolysis. After that, once we get into, several minutes to hours of length, now we're gonna have this combination of Krebs, ETC, and beta oxidation. What happens here, when we see this line dropping down, this means that we're running out of carbohydrate. And that's why beta oxidation takes off. So let's write in here that beta oxidation is burning of fat. Okay, now we're gonna start getting into the nitty-gritty. So what I told you was that we're gonna be taking glucose and fats, and then from these substances, we're gonna be taking electrons, okay? Electrons have energy. Now we're gonna have to take these electrons out of these foodstuffs, okay, and we're gonna be using these electrons to make ATP. But before we can do that, we gotta transport these electrons from where they're taken all the way into the inner part of the mitochondria. And we're gonna have substances that will actually take them in there. Okay, so we're gonna have these substances that are called electron carriers. And there's two different kinds of electron carriers, and we'll discuss these in just a second. But what we're going to talk about here is the transfer of electrons from one substance to another substance is what we call a redox reaction. Two different reactions. One of them is oxidation. The other one is reduction, and they always happen together. You can't have one without the other. Let's start off with oxidation. If something loses electrons, it has been oxidized. So when glucose and fats lose electrons to these electron carriers, those substances have been oxidized. They've been robbed of electrons. Mm-hmm. So when glucose and fat have electrons taken from them, they're being oxidized. Okay. On the other end, these electron carriers that are taking those electrons away, they're becoming reduced. So the electrons are coming off of glucose and they're going straight over these electron carriers, and the same thing is true for the fats. They're donating electrons to these electron carriers. Easiest way to remember this: if you gain more electrons, what happens to your overall charge? So if you're neutral and I get a bunch of negative charges, I'm going to become more negative. My overall charge is going to go down. Okay, so the thing that is actually gaining electrons is being reduced. That's how I would remember this. Whatever it is that's gaining an electron is becoming more negative, because electrons are negative. So its overall charge is being reduced. Okay, so let's look at sodium and chloride. You guys are taking basic chemistry, at least at the high school level. What number of electrons do all atoms want to have in their outer shell? In the first shell, you're right, it's 2, but anything after the first shell, how many do they want to have? 8. They want to have 8. That's the most balanced form they can be in. It's called the octet rule. All right, for chlorine, its outer shell has 7. So clearly it wants to gain 1 more. And then for sodium, its outer shell has just 1. And then there's another shell below that that's complete at 8. So this is in a very really unstable form to be in. If we put these two together, what's going to happen? This electron is going to leave, and it's going to go over here and pair up with this one. Okay? Now the overall charge of chlorine now is going to be -1. The overall charge of sodium now, because it's lost an electron, is going to be +1. If we put sodium and chlorine together, they're going to make table salt. Okay, they'll form an ionic bond. So, from this, which of these two substances was reduced? Which one became more negative? Chlorine did. So this is the reducing agent. Or actually it was the oxidizing agent. It became reduced. Let's just stick with that. What happened to sodium? It became oxidized. Okay, it was oxidized. It lost an electron. Chlorine gained an electron, so it's reduced. This thing happened together, so combined, this is a redox reaction. Questions? Okay, this redox reaction is almost always going to be catalyzed by enzymes. What does a catalyst do? Speeds up the process. And it doesn't get changed itself as a result of the process. Now, an enzyme is a biological catalyst. Okay, so here we go. We said that we had 2 different electron carriers biologically. Here are the 2 different ones. We have FAD and we have NAD+. This is the oxidized form of the 2 different electron carriers. FAD and NAD+. Each one of these, FAD and NAD+, can carry 2 electrons. They can each pick up 2 electrons. When we reduce FAD, we turn it, if we look here, picks up 2 electrons, it happens to pick up 2 hydrogen ions too, but what we're really caring about is this, and we turn this into FADH2. So oxidized, now reduced. So this one has been fully charged up with these electrons that we've stolen from glucose and from fat, and now we're going to transport it to a different location. And we're going to take the energy out, and we're going to use it to make ATP. So these are like battery carriers. We're taking them from here to a different location. The other one, NAD+, it picks up 2 electrons and 1 hydrogen, and we make NADH. This is now reduced, because we've grabbed 2 additional electrons. Okay, so those are our 2 electron carriers. FAD and NAD+, and we turn them into FADH2 and NADH. Questions? You have a question? Oh, I don't believe it. Brooke? Question? No?
Is this happening before, before the AP process, or
Before the what process?
The active potential, like when we go to.
Oh, this is happening constantly.
Okay.
Even if you're not contracting your muscles, you're still making and burning ATP.
Okay.
Okay, and in order to make that ATP, we still have to make these so that we can transport electrons from wherever we're burning our fats and carbs to where we're finally gonna be making our ATP.
Okay.
Okay? Good question. All right. So, that's redox. Now, let's move on to the next one, phosphorylation. Okay, the next reaction that we have to concern ourselves with is phosphorylation. Phosphorylation is real simple. Adding a phosphate group to something. That is what phosphorylation is. So let's write that down. The definition of phosphorylation is to add a phosphate group to something. Now, what do we want to add a phosphate group to? Let me ask it a different way. What are we trying to make at the final product of all this process? Okay, so you said it, but what are we trying to make right now? ATP. So what are we going to add a phosphate group to, David? We're gonna add a phosphate group to a DP to make ATP. Okay, that is the only phosphorylation that we really care about. We have to rephosphorylate ADP to make it back into ATP. Okay, it's a constant cycle. We're always recycling this stuff. Let me ask you another question. If you stopped metabolizing your foodstuffs right now, if you stopped making any ATP right now, how long do you think you'd actually live? How much stored ATP do you think you have? In terms of time. Can't hear you.
Isn't it like 3 days?
Not even close. 2 seconds. You have 2 seconds worth of ATP available to you at any given time. That's how rapidly we have to be recycling this stuff. Always have to be recycling this stuff. Okay, there's 2 different kinds of phosphorylation. There's what's called substrate level phosphorylation, and then there's oxidative phosphorylation. Now, oxidative phosphorylation happens in one place only, so let's write that part down first. Oxidative phosphorylation will only happen in the mitochondria. And that's not the end of the sentence, but let's write that down first. Oxidative phosphorylation will only happen in the mitochondria at the end of ETC, the electron transport chain. Oxidative phosphorylation will only take place in the mitochondria at the end of the electron transport chain. Okay, substrate level phosphorylation can take place in a couple of different locations. So let's write down where this takes place. We can have substrate level phosphorylation take place in the phosphagen system, in glycolysis, and in Krebs. I will. Substrate level will take place in phosphagen, glycolysis, and Krebs. All right. Now let's show what the difference is between the two. Here we have 2 things that are in the middle of a chemical reaction, and coming at the other end, we're going to end up with NaCl. Over here, on this side of any chemical reaction, we have products, and on this side, we have substrates. Okay? These are the substrates, that's the product. So in substrate level phosphorylation, we have a phosphate group that's already attached to a substrate. It's attached to something. And we're going to be taking it off of whatever that something is and putting it onto ATP. So let's see an example. Here's an example. Here's our biological catalyst, it's an enzyme. And here we have our substrate. See how it's already bound to that phosphate group? The There's all the squiggly line, it's already attached to a phosphate group. And what else do we have in here? We have ADP. So what are our substrates? Our substrates are whatever this substance is and ADP. Okay, so that enzyme is going to plug that phosphate group off of the substrate and put it onto ADP, and then what are we going to get on the other end? ATP. And whatever this product is. Okay, so for substrate level phosphorylation, the phosphate group has to already be bound to a substrate. I'll say it a couple times. For substrate level phosphorylation, the phosphate group, right here, at the beginning of the reaction, has to already be bound to a substrate. Yes? Mhm. For substrate level phosphorylation, the phosphate group at the beginning of the reaction has to already be bound to a substrate. In other words, we're robbing this phosphate group from something. Questions? All right, so let's see a real world example of this. This is the phosphagen system. This is it. This is the phosphagen system. The substrate in the phosphagen system is right here. This is creatine with a phosphate group added onto it. PCR stands for phosphocreatine. Okay? Phosphocreatine. So let's say that we're starting off with ADP, we need to turn it into ATP. We're going to take the phosphate group off of phosphocreatine, put it onto ADP, and make ATP. And what do we have left over? Just free creatine. Yes? Okay. Here's what we're starting with. These are the substrates of our reaction. ADP, which we know we need to turn into ATP, and then we have phosphocreatine. Here's our phosphate group added to creatine. Okay, then we're going to have an enzyme, just like we had in the previous slide. Here's our enzyme. In this case, the enzyme is creatine kinase. How do we know this is an enzyme? Creatine kinase. It ends in ACE. And creatine kinase is responsible for taking a phosphate group off of phosphocreatine, putting it onto ADP, and now we have ATP. And what do we have left over? Just free creatine. Okay, so we've physically removed a phosphate group from phosphocreatine and stuck it onto ADP and made a new ATP. Okay, now this pathway, is it aerobic or anaerobic?
Aerobic.
Nope.
Anaerobic.
Anaerobic. Doesn't require oxygen. Where does it take place in the body? Or where does it take place in the cell?
Mitochondria.
Nope.
I lied.
Cytoplasm. If it's anaerobic, it's going to be the cytoplasm. Remember, the mitochondria are oxidative organelles. That's where our oxygen is going to be. So all the things that take place in there have to be aerobic. Okay. So, whenever we do stuff like a box jump, okay, throwing a baseball, throwing a punch, sprinting from here to the end of the room, we're burning through a lot of ATP, and we need to rephosphorylate that ADP very rapidly. We're going to utilize this pathway to do that. Okay? So let's take a look at this. This is a test question slide. So get your thinking caps on. What we have here is percent of our resting value. So if we're at rest, we have this much ATP and we have this much phosphocreatine sitting in our cytoplasm of our muscle cells. All right, And then this is time in seconds of doing super maximal effort. Okay, as hard as you can possibly go. What do we see happen here? First of all, how long does this activity last? About 14 seconds, and we reach exhaustion. So this would be like an all-out sprint on a treadmill or on a bike, as hard as you can pedal those pedals. What do we see initially? We see a pretty big drop in ATP levels that last for about 2 seconds. Okay, that represents the 2 seconds worth of ATP that we have in store at any given time. We use that immediately. And then all we have left over is ADP. So we have to rephosphorylate it very quickly. Okay? So we have 2 seconds worth of ATP that we burn through in 2 seconds, and that's why this number dips. But then look what happens. Instead of just keep on coming down, it plateaus. And it stays really nice and constant for about 8 seconds. And what's happening there is this process. Okay? For 2 seconds worth of our maximal effort, we burn through all of our ATP, and all we have left is ADP. But we have phosphocreatine sitting there ready to go, and it's ready to hand off its phosphate group to ADP to turn it back into ATP. Okay, so that's what happens. We level out for about 8 seconds, and then the ATP levels start to drop again. Why do the ATP levels plummet at the end? What do we run out of?
ATP.
Well, we have plenty of ADP. Say again?
Creatine.
What kind of creatine? Not free creatine.
Oh, phosphocreatine.
Phosphocreatine. We ran out of phosphocreatine. All we have left is ADP and free creatine. Okay, so we reach the point of exhaustion. You're looking up and looking back. Looking up and looking back. That means you're not getting it. Say something.
I'm just, okay, so like, the blue line's ATP and the red line's the.
Phosphocreatine.
Right?
Uh-huh.
So you were explaining like the ATP process, and then, like, I just don't get how the phosphocreatine like correlates on the ground. Like, I don't get.
So if we're losing, we burn through all of our ATP very quickly, and all we had left over now is ADP. How are we going to turn that ADP back into ATP?
By the end of the process.
By taking the phosphate group off of the phosphocreatine. So here we start off with the phosphocreatine levels at 100%, and then they really start to plummet because all of those phosphocreatines are rapidly handing off their one phosphate group to ADP to keep our ATP levels as high as they can, until we have no more phosphocreatine left, and then they go. Now we can keep exercising, but the intensity of that exercise is gonna have to change, because we're gonna have to shift to the next energy pathway, which is gonna be glycolysis, and it can't run this fast.
So the red line, the phosphocreatine is just kind of like, it's like giving it like a handoff, saying like,
Yeah.
here's phosphate, like, we can take this.
Exactly, it's
Okay.
sacrificing itself so that it can keep ATP levels nice and high.
Okay.
It's exactly what's happening. All right, so this begs the question, why would we want to take a creatine supplement? What do you think would happen to this particular figure if we had additional creatine in our body? Yeah, I can't hear over the background noise. Louder?
It would last a long period of time.
What would last a long period? Okay, well, both of these would, right? Because we'd have more phosphocreatine to begin with, so then this line would probably go out to another 2 or 3 seconds before it drops off. Okay, and if you're talking about an event that's 10 seconds long, and you need to beat the person next to you by 100th or 200ths of a second, that little extra bit of maximal effort might make the difference between first and maybe even dead last. Okay, so there is quite a bit of scientific evidence that it helps you maintain maximal effort for a longer duration of time. Questions on that part? This is a test question. Yes?
So from 2 seconds to 10 seconds, it's stabilizing by sacrificing the PCR? Is that-
By the phosphate group specifically being removed from this creatine. And now all we have left is just that free creatine now. We've used up all this. to rephosphorylate ADP to ATP, okay? Now, once we've stopped and we've recovered, then we can rephosphorylate this and this to go back to resting levels. But after we get done with exhaustive exercise, we're gonna have to lay there for a little while and wait until we're able to rephosphorylate everything. Okay, that's recovery. All right, let's move on. And let's move on now to oxidative phosphorylation. Let's see what this looks like. Okay, once again, where is this gonna take place? Only one place. Where in this cell will this take place? The mitochondria. Take place in the mitochondria. And what did I say about the mitochondria? That's where oxygen goes. So everything that's in there is oxidative, which means it's aerobic. Okay. Look here at ADP and inorganic phosphate. This inorganic phosphate isn't attached to anything. Now it's free floating. So unlike substrate level phosphorylation, where it has to be attached to something first, with oxidative phosphorylation, that phosphate group is just free floating. Okay? We have ADP and this free floating phosphate group, and they get stuck together to make ATP. And this is done by an enzyme called an ATP synthase. Pretty straightforward name there. We know exactly what it does. It synthesizes ATP. Now, where it gets the energy to do this, we will find out shortly. Okay, so it's very different from substrate level phosphorylation. That phosphate group is not attached to anything at the beginning of this reaction. It's just sitting there. Questions?
You said the synthase does what to the ATP?
Phosphorylates ADP. The
Okay,
synthase
okay.
takes these two, puts them together, and makes this.
Okay.
Okay, questions? All right. So we can see here, here's our phosphagen system. Here's glycolysis. They're taking place inside the cytoplasm, and they are anaerobic. Okay, we look at the mitochondria nice and up close. We have a very complex looking structure here. It has an outer membrane, and it has an inner membrane, and then it has a space between those two membranes called the intermembrane space. And then the very interior of a mitochondria is called the matrix, just like the movie. And what do we have in here? We have the Krebs cycles in here, beta oxidation is in here as well. And then we have one more, and add this to your notes, because I didn't write it on this picture. We have the electron transport chain, ETC, that takes place on the inner mitochondrial membrane. Okay, so on this membrane that's right here, all of those enzymes that are part of the electron transport chain, they're located on the inner mitochondrial membrane. Say it louder, can you hear me? On the inner mitochondrial membrane. This says inner membrane here, all along here. Okay. Now we're getting into our fun stuff here. So, phosphagen is kind of like off by itself. It doesn't require carbohydrates and fats. It's going to be utilizing that creatine system only. Okay, so we utilize that for very specific types of activities. Really short duration, high intensity ballistic activities. Everything beyond, let's say 10 seconds is now gonna start to utilize carbohydrates and fats. And in terms of which is gonna happen first, it depends on the intensity of the exercise. If it's really low intensity exercise, we're always gonna be using a combination of both fats and carbohydrates. But we'll use a little bit more fat during low intensity exercise than we will carbohydrate. And then as we shift over to high intensity, we're gonna use less and less fat and more carbs. But let's see how they're all linked together. Each one of these energy pathways is gonna utilize substrates and then make products, because it's one big, long chemical reaction. Substrates to begin with, this is basically our raw ingredients, and then products on the other end, this is what we produced, okay? For each one of these pathways, whatever the products of one are, they get handed off to the next energy pathway. Okay, it's like an assembly line. So we're making cars, let's think of it that way. All right, so who's credited with making the first real assembly line? The guy who made trucks? Ford. All right, so the first thing that we're going to be putting together on our car is going to be the chassis. So here's our chassis. And then the chassis is going to be handed off to the next group in the assembly line, who are then going to put on the wheels. And then that's going to get handed off to the next group in the assembly line that's going to put on the body. So then we're going to have the body of the car with our windows and our wheels. Looks nothing at all like a car, but that's as close as we're going to get, okay? All right, so one energy pathway is going to hand off to the next, to the next. Same basic premise is going to happen here. The things that we make at the end of glycolysis are going to feed into Krebs. When we get done doing Krebs, the things that we make here, we're going to hand off to electron transport chain. If we look at beta oxidation, we're going to take fats and we're going to start to chop those up. And the things that we make in beta oxidation, we will hand off to both Krebs and also electron transport chain. So all of these energy pathways are linked together. The stuff that you make, I'm going to use here. And then when I get done with this, I'm going to hand it off to you. And there's a final, last part of the assembly line. And the last part of the assembly line for all of these energy pathways is the electron transport chain. So I'll write that down. ETC is the last part of the assembly line. I guess we call it disassembly line, since we're breaking down carbs and fats. Okay, so the stuff that we produce in glycolysis goes into Krebs. The stuff that we produce in Krebs goes to ETC. Beta oxidation is a little funny. It hands stuff off to both Krebs and also directly to ETC. Whatever goes to Krebs is eventually going to end up back at ETC. And you can see what we get out at each of these stages. ATP, ATP, ATP. Okay, so we make a teeny little bit of ATP during glycolysis. We make a teeny little bit during Krebs. And we make a boatload of ATP at the end of electron transport chain. So a little bit here, and then the rest of it gets made at the end of ETC. Okay. So we have this person doing low intensity exercise. And we can see here that we've got Krebs and beta oxidation running effectively 50-50. Okay? Now Krebs is getting some stuff from beta oxidation, but in this case it's getting quite a bit from glycolysis as well. If we change from low intensity exercise to high intensity exercise, we're going to shift away from fat over towards carbs. So what's going to happen here is that we're going to see glycolysis is be contributing a whole lot more to Krebs than beta oxidation is. The higher the intensity of the workout, the less fat we're going to be burning. Yes?
I have a question, why, so when people are trying to burn fat, why do they do like HIIT exercises and things like that?
Very good question. Because you would think that there's a fat burning zone. Now, if you read the book that I just published a couple months ago, you'll read that whole section in there. There's no such thing as a fat burning zone. It's total bullshit. Even when they put it on the treadmill, it says, stay right here in your fat burning zone. Utter nonsense. You don't burn fat or carbohydrates necessarily, what you're burning are calories. The higher the intensity of the workout, the longer it's going to take you to recover after that workout. And it's during that recovery phase, once we come back down, that we shift over again to using fats. Okay, now, if you work out at high intensity with very low carbohydrates in your system to begin with, the only fuel you have is fat. Okay, so calories are calories are calories as far as your body is concerned. It's burning fuel. Okay, so HIIT exercises are great because they burn the whole lot more calories in a really compact amount of time. And the whole purpose is to keep you at really high intensities the entire way through. Okay, so when I ask people, do you exercise? They say, I want to lose weight. Okay, do you exercise? Well, I walk. That's not close to being good enough. Okay, you have to be at 80, at least 70, probably more like 80% of your max heart rate for at least a half an hour. Now you take little breaks in between, but the purpose of that is that once that workout is done, we have to recover from that workout. We gotta clear out all the lactic acid that we produce, we gotta get rid of all the CO2 that's in our blood, and all of that requires us to metabolize more foods. And at low intensities, now during recovery, the one we're gonna choose the most is fat. Okay. So the purpose of the workout is not to burn the calories then, it's after.
So it's true when they say that like it's still burning whatever after you're done with the workout?
Yes. The higher the intensity and the longer it goes, the longer that recovery period is going to take. Okay, so HIIT workouts are great for that purpose. And especially if you have people who have very busy schedules, right? Getting an hour and a half workout, I don't have the time. So as soon as I get home, I go to my garage, I pull out my spin bike, and I get my weight set, and I do a 30-minute circuit as hard as I can possibly go, and then I'm done. And then I can go play with my daughter. You know, but if you're younger, those things are built into your life. The older you get, it's hard to actually schedule that stuff. Good question, David. All right, glycolysis, let's get to it. We're gonna get to glycolysis, and we're gonna get through the other carbohydrate stuff, and then we'll hit beta oxidation next time. Glycolysis, it is a 10-step anaerobic pathway that occurs in the cytosol, the cytoplasm. We start with glucose and we end with 2 molecules of pyruvic acid. I'm going fast because you're going to see this over and over again. 3 major phases: sugar activation, sugar cleavage, and sugar oxidation and ATP formation. We'll get to those in a second. Let's take a look at this. I don't want you to memorize this chart. What I want you to pay attention to are the number of carbons, and then I want you to keep a tally for ATP. So let's get started. Each of these circles represents a carbon. So how many carbons does glucose have? 6. All right. So let's go through our phases here. We start with a 6-carbon molecule, and the first thing that we're going to do is we're actually going to phosphorylate it. We're going to burn an ATP to get this process started. So we're already at a negative. This isn't good. Okay, this is what we call priming the pump. Okay, and in order to get that water pump going, you got to dump a bucket of water in there first to get it going. Another way to think of this is you got to spend money to make money. Okay? So we've already burned off 1 ATP. We're -1 so far. Now we have a 6-carbon compound with 1 phosphate group attached. We're going to move down here to step 3. We're going to use another ATP. Now we're at -2. And we have a 6-carbon compound with 2 phosphates attached. That's where we are right now. Now, this portion 1 through 4 just happens 1 time. But then everything after that, from here on, we run it twice. Because we're going to take that 6-carbon molecule and we're going to break it in 2. And then each one of those is going to go through the second half of glycolysis. Starting off here with 6, we split it in 2. This one's going to go through here, and then this one's going to go through here. So that's why these portions here, they run 2 times, not just once. Because we have 2 halves that have to go through.
So why is the second line of carbons with the phosphate added and the third line of carbons with the phosphate added? Why is that the same?
It's what we call an isoformation, it's an isomerase change. We're taking, I don't want to get too far in the weeds here. The chemical formula is the exact same, the structure's changed.
Okay.
So we have an enzyme that has changed the structure of the molecule. Okay. But that's as much as I want you to know about it. From 1 through 4, this happens 1 time. Steps 5 through 10, 2 times. And that's why each one of these things that you see here, there's a 2. Okay? Each of the halves has to go through this process. All right, so we'll move up here. Now we have a 3-carbon molecule with a phosphate group on it, and we're going to add another phosphate group to it. And in this process, look what happens. We convert NAD plus to NADH. Okay, so when we go from here to here, we've added another phosphate group to our 3-carbon molecule, and we've converted NAD plus to NADH. So what happened from here to here?
They lost an electron.
What
No.
did? No, you're right,
Yeah.
something lost an electron, what did?
The NAD.
Ah,
The NAD.
it gained electrons and it took it from this. So what happened to NAD plus to make it into NADH? It got reduced. It gained electrons. The NAD plus took electrons from this 3-carbon molecule, from this sugar, okay, and we turned that into NADH, and this we're going to use later to make ATP. We have to transport it to a whole other location. Right now, we just put a bunch of energy into it. So this is our high energy electron carrier. It's carrying the energy of those electrons to another location. All right, we move on. We have a 3-carbon molecule now with 2 phosphate groups. And look what we do here. We actually make 2 ATP. Sweet, we finally made some. Now, what kind of phosphorylation is this to go from ADP to ATP? Is it oxidative or substrate level?
Substrate.
Substrate, because it's already attached to that 3-carbon molecule. And also, the only place that we do oxidative phosphorylation is in the mitochondria, and this is in the mitochondria. All right, so we have now got 2 ATP that we've formed, and we have 2 3-carbon molecules still with a phosphate group on it. We come all the way back down to here, and we make 2 more ATP by substrate level phosphorylation, and we're left with 2 pyruvic acids, each of which have 3 carbons. So we started with a glucose that had 6, and at the end we have 2 pyruvic acids, each of which have 3 carbons.
Is that just because it?
Because we split the thing in 2.
Okay.
Okay? What else do we make? We made 4 ATP, but we burned 2 here. So what we're going to concern ourselves with now is the terminology of accounting. Gross versus net. What is your gross salary? With the total that you actually get paid, and then after Uncle Sam takes his cut, what do you have left? Your net. All right, what was the gross ATP production from glycolysis? 4. The gross is 4 ATP, but what's our net? 2, because we had to burn 2 to start. Okay, so it's not a very efficient process so far. Audrey, question? No, you're good? All right. So at the end of this, what do we have? We have 2 NADHs, which we can use later. We have 2 net ATP, and then we have 2 pyruvic acids, which still have a lot of energy. Okay, so we're gonna have to get some more energy out of those. So this is gonna get handed off to Krebs cycle. So we're going next, the next step in the chain. Questions on glycolysis first? All right, here is Krebs cycle. I know it looks horrible, but it's really not that bad. Now let's keep track of the number of carbons. What do we have at the top? We have pyruvate. So this is still in the cytoplasm. And where is all of this? Where's Krebs cycle located? In the mitochondrial matrix. So we gotta get pyruvate through the outer membrane and through the inner membrane to get it in there. Okay. Now, here's what I want you to write down on this. We're gonna keep track of our carbons. Oxaloacetate. Don't memorize the name, just memorize the number of carbons. Oxaloacetate has 4 carbons. So write that down. Oxaloacetate, right here, has 4 carbons. Citrate, here, that has 6 carbons. Citrate has 6. Okay. To get from 4 to 6, we're going to have to add 2. How many carbons does pyruvate have?
2.
No. Come on,
3.
we just did this. 3. So we're going to have to chop off 1 carbon. We're going to have to take that pyruvate, which has 3 carbons, and chop off 1. Okay? And when we do that, we make what's called an acetyl group. So write this down. Acetyl, this word here, A-C-E-T-Y-L, that is a 2-carbon compound. That's your definition of it. An acetyl group is a 2-carbon compound. Okay, so where did that extra carbon go? We have pyruvate, which is 3. We turned it into an acetyl group, which is 2. Where did the other carbon go? It's right here. Carbon dioxide. Okay, we chopped it off and we made a carbon dioxide. And in the process, look what else we made. An NADH, which we can use later to make ATP. Okay, so far we're doing pretty well. All right, so our acetyl group joins up with oxaloacetate to make citrate. 4 plus 2 equals 6. All right, let's move on. We're going to change citrate to isocitrate. This is another one of these conformational changes. Doesn't change the chemical formula at all. And then look what happens here. We're making another NADH. Awesome. We can use this later. Isocitrate gets changed into alpha ketoglutarate. Isocitrate, 6 carbons. Alpha ketoglutarate, 5 carbons. Isocitrate has 6. Alpha ketoglutarate has 5. So, look what happens. We chop off another carbon. Right there, chop off another carbon. So alpha ketoglutarate is now 5 carbons. All right, we're going to go from alpha ketoglutarate to succinyl-CoA. 5 carbons to 4 carbons. We chop off another carbon dioxide and we make another NADH. This is all good. We're extracting more and more energy from this remnant of glucose. All right, the rest of the way, succinyl-CoA to succinate to fumarate to malate to oxaloacetate, all of these, we stay at 4 carbons the whole way. The only thing that we're doing along the way is sucking out some more energy. So we can make an ATP here by substrate level phosphorylation. We make an FADH2 here, and then we make an NADH here. That's one cycle. Now we're back to the beginning. All right, I've got a question for you. For every single glucose molecule, how many times are we going to turn Krebs?
Twice.
That's right.
Oh, I guess.
Okay. One glucose molecule is 6 carbons. We split it in 2, and each one of those pyruvates goes through Krebs. So write it down. For every glucose molecule, we get 2 turns of Krebs. For every glucose molecule, we get 2 turns of Krebs. All right, let's see what we make here. Right there at the top, right about here, we make an NADH. I want y'all to draw this picture as well, please. Right here, we make another NADH. Okay. And then down here, we're going to make an ATP by substrate level phosphorylation. And then here, we're going to make an FADH2. And then here, we're going to make another NADH. So for our final tally for each turn of Krebs, all I'm asking for is per turn of Krebs. That's what we're trying to figure out here. Per turn of Krebs, what do we make in total? We make 1, 2, 3 NADH. We make 1 FADH2. And we make 1 ATP. Everybody with my counting so far? All right. Now, let me add our conversion table. Every NADH2, or NADH rather, equals 2.5 ATP. When we convert these, we get 2.5 ATP per. For every FADH2, 1.5 ATP.
And
Alright.
this is for, what did you say this was for again? Those, like for every what, you get 2.5 ATP?
For every NADH, you get 2.5
Oh,
ATP.
okay.
Okay, we got 3 NADH with every turn of Krebs. 3 times 2.5 is 7.5. Okay. We get 1 FADH2. 7.5 plus 1.5 is 9. And we get 1 ATP. 9 plus 1 is 10. So, for every turn of Krebs, we always get 10 ATP. You want to go through the math again?
Yes, please.
We know that we get 3 of these. For each one of these, we get 2.5 ATP. So 3 times 2.5 is 7.5. We get 1 FADH2. That's worth 1.5. 7.5 plus 1.5 is 9. And then we get 1 ATP directly. 9 and 1 gives us 10. Questions?
It goes through this cycle twice, right?
It does, but all I'm calculating right now is
Is
per
one
turn.
Okay.
But you're right, and we're gonna get to that part specifically in just a second. When we completely metabolize 1 molecule of glucose, we have to count that twice. But right now, since we're gonna be using this for both glucose and fats, all I wanna know is every time I turn Krebs, how many ATP am I gonna get out? 10. Okay? Okay, we got 3 minutes left, we're gonna use it. Check this out, another one of my awesome animations that I make. You can watch this as many times as you need to. You just actually have to run the PowerPoint. All right, we're gonna take our 6-carbon sugar, split it into 2 pyruvates that are 3 carbons each. In the process, we'll make a net of 2 ATP and 2 NADH. Okay, now each one of these pyruvates is gonna go into the Krebs cycle. So let's pick one. We're gonna shuttle this across, and we gotta chop off one of those carbons. Now we have citrate, just 6 carbons. And we made a CO2, and we made an NADH here. Now this one we have not counted into the mix yet. It's separate from Krebs. We have 6 carbons, we gotta get back over here to 4, so let's keep going through this. We go through the process, chop off another carbon, make an NADH. Chop off another carbon, make another NADH. We start to rearrange the shape of this molecule, although we don't really do anything to it special. We're now making an ATP here. We make another FADH2 here, and we make another NADH here, and then we're back to oxaloacetate. We're ready to take in another acetyl group. It's cycle. It goes back to the beginning every time. Questions? Last slide that we're gonna cover today, let's take a look at this. Okay, from glycolysis, we get 2 ATP directly, and we get our 2 NADH. Each of these is worth 2.5, so now we have 2 and 5 so far, okay? Now, I shouldn't really put this in here as being from Krebs because this number should really only be 6. Because we get 1, 2, 3, 2 times, that's 6. But what I'm counting is that extra NADH that we make between glycolysis and Krebs. When we take the pyruvate and we have to chop off that first carbon. That's now added into the mix, here. So we make 2 ATP directly, we make 8 NADH in total, and 2 FADH2s, because like you said, every time that we go through a single molecule of glucose, we have to turn Krebs twice. So if we add all of this up, we get 32 ATP. So that is the number that I want you to write in your notes right now. If we fully metabolize 1 molecule of glucose, we get 32 ATP. If we fully metabolize 1 molecule of glucose, we get 32 ATP. That number is set. Doesn't change. With fat, it's gonna change because fats can be different lengths. Glucose is always 32. If you completely metabolize glucose, you get 32 ATP, period. Questions?
What's the GTP?
That's actually what we turn, if we go back, we go way back. Here. Initially, we actually create GTP, which is, so we have adenosine triphosphate, we have guanosine triphosphate as well. It's just a different form.
Okay.
And then we can turn that into ATP just as quickly.
Is that something you have to worry about?
Nope.
Okay.
That's why I didn't mention anything about it. But it's good that you're picking these things up. Okay. All right, so 32 is your number. That's where we've gotten so far. Now we haven't touched ETC yet, so we don't really know how we're making this 2.5 or 1.5 from our electron carriers, but we'll find that out on, what is today? Monday. See you Monday. Have a great weekend. If you have any questions right now,